Okay, as we continue to learn about reflection, we've seen that with flat mirrors, we see the law of reflection, that the angle of incidence, the incoming ray, and the angle of reflection, the outgoing ray, are equal. And if you stand in front of a flat mirror, your image will be an equal distance behind the mirror. Now let's look at curved mirrors. Curved mirrors come in two shapes. They can be concave, like you're going into a cave, or they can be convex. And what I'm showing here is 5 parallel rays coming into this concave mirror. These parallel rays could be light coming from a distant source, so that by the time it hits the mirror, they are approximately parallel. Either way, when the light rays hit this mirror, they will bounce off each little section of the mirror according to the law of reflection on the other side of the normal line, and so this ray might bounce back like so, this ray might bounce back like so, and so on and so forth, and we get a point where these light rays converge. That point is called the focus, or the focal point. For a concave mirror, the focal point has a positive value, so it's a positive f. More sharply curved mirrors will have shorter focal lengths, or a closer focal point. If the mirror is very gently curved, it's almost flat, then the focal length is much greater. However, if you take the other side of the curve and you put your reflective surface on the convex side, you get a convex mirror. Now when this ray strikes the mirror surface, instead of it bouncing inward, it will bounce outward. And the result is that this one goes straight back. These light rays spread out. So it appears that there is no focal point. However, if we imagine these lines radiating back to some invisible point behind the mirror, there is a focal point back here. It is a negative focal length. There are other words that you can use to describe these. Concave mirrors are convergent. Convex mirrors are divergent. Concave mirrors cause parallel rays of light to come together. Convex mirrors cause parallel rays of light to spread apart. Okay, unlike a flat mirror, where the image will form behind the mirror exactly the same distance away, if you stand in front of a curved mirror, your image could form in a variety of different places. In order to find that, we need to get some terminology down here. First, we have F, our focal point, but we also have a point called the CC, the center of curvature. If we imagine this mirror surface as something like a circle, that circle would have its center at the CC. So the distance from the CC to the vertex would be 1 radius. The CC is also twice the focal length. So if the focal length is 15 centimeters, the CC is 30 centimeters. Okay, let's define a few other things here. If my object has a certain height, we call it ho, height of the object. And whatever distance my object is from the mirror, we call that do, distance to the object, or object distance. Well, as we'll see, an object placed in front of a curved mirror will form an image. In this case, the image might look something like this. And unlike a plane mirror, the image distance is not the same as the object distance, and the height of the image, high, might be different from the height of the object. So if we want to relate the distance that an object is from the mirror to the distance that the image is from the mirror, we have an expression for this. Just think, if I do I die. 1 over the focal length equals 1 over the object distance plus 1 over the image distance. If you know 2 of these values, you can find the third. But if we want to relate the height of the object to the height of the image, we have an expression for this as well. Just think of the 7 dwarves. Hi-ho equals negative di-do. The height of the image and the height of the object are equal and negative in proportion to the distance to the image and the distance to the object. So knowing some of these values will enable us to find where the image forms as well as how big the image will be. We'll see some examples of this in the next video.